So we're going to go through a few more examples using the ratio test. And just to remind you what we're talking about, the ratio test states that if you look at the ratio of two consecutive terms, something of the form an plus 1 over an in absolute value, and you look at the limit, if the limit exists and is less than 1, then we have an absolutely convergent series. If the limit of this absolute value of the quotient of two consecutive terms exists and is greater than 1, or if this sequence of ratios goes to infinity, then the series is divergent. And if the limit is exactly 1, we cannot conclude from the ratio test, and that means you need to use another criterion. So in the previous video we've seen how to apply this ratio test to conclude about the convergence of various series. We're going to go through a few more examples, starting with a series of n factorial over n to the n. So if I look at the ratio of two consecutive terms, an plus 1 divided by an, when I replace n by n plus 1, I get n plus 1 factorial divided by n plus 1 to the n plus 1. And then I multiply by the reciprocal of the of an, which is n to the n divided by n factorial. Now I have n plus 1 factorial that I divide by n factorial. So at the top I have the product of the n plus 1 first integers, at the bottom product of the first n integers. They all cancel out except n plus 1 at the top. And then this n plus 1 to the n plus 1, I can write it as n plus 1 to the n times n plus 1. And so what remains is n to the n at the top, n plus 1 times n plus 1 to the n at the bottom. You see that one of the n plus 1's cancels out, and what remains is n to the n over n plus 1 to the n, which I can write n over n plus 1 to the power n. And what we're interested in is the limit of this ratio. And to find the limit, here we have something where the variable n is both in the base and in the exponent, so the natural thing to do is rewrite that as a power of the Euler number e. Specifically, it's e to the n natural log of n over n plus 1. So to find the limit of our ratio, we need to find the limit of n ln of n over n plus 1. And of course, the limit as n goes to infinity is the same as the limit as x goes to infinity of natural log of x over x plus 1 divided by 1 over x, which is the same as multiplying by x. Under that form, when x goes to infinity, what's inside the log goes to 1, which means the top goes to natural log of 1, which is 0. And the bottom, 1 over x, goes to 0 as well. So we have an indeterminate form of the type 0 over 0. And we can lift the indetermination by using the rule of de L'Hopital. And the limit is the same as the limit of the ratio of the derivatives. The derivative of natural log of x over x plus 1 is 1 over whatever I have inside the log, which is x plus 1 over x, multiplied by the derivative of what I have inside of the log. And to get this derivative, I use the quotient rule, so I get 1 times x plus 1 minus 1 times x, so x plus 1 minus x, divided by the bottom squared, x plus 1 squared. The derivative of the bottom, on the other end, I differentiate 1 over x, I get negative 1 over x squared. So now you see that at the top I have this x plus 1 divided by x plus 1 squared. One of the x plus 1 cancels out. I'm going to have just x times x plus 1 at the bottom. And then here x plus 1 minus x is just 1, so at the top I have 1 over x, x plus 1. And I divide that by 1 over x squared, negative 1 over x squared. So it's like multiplying the top by negative x squared. And therefore I get negative x squared divided by x, x plus 1. And I'm looking at the limit of this as x goes to infinity. At the top I have polynomial of degree 2 and leading coefficient negative 1. At the bottom, a polynomial of degree 2 of leading coefficient 1. So the limit is negative 1 over 1, negative 1. And so, because my ratio an plus 1 over an in absolute value was e to the n ln of n over n plus 1, and the limit of n ln of n over n plus 1 is negative 1, the limit of my ratio is going to be e to the negative 1, which is 1 over e, and e is greater than 1, so the reciprocal is less than 1. So the limit of my ratio of two consecutive terms is less than 1, and by the ratio test I can conclude that the series is convergent. For the second exercise, we want to decide whether the series of general term n factorial e to the negative n is convergent. And because we have a factorial and a power, it is natural to use the ratio test, so we can look at an plus 1 over an. An plus 1 is n plus 1 factorial multiplied by e to the negative n plus 1, and we divide that by an, which is n factorial e to the negative n. Of course, n plus 1 factorial over n factorial, we have at the top product of the first n plus 1 integers, at the bottom product of the first n integers, so the first n integers cancel out, what remains is just n plus 1 at the top. And then we have this quotient e to the negative n plus 1 divided by e to the negative n. So at the top, I can write that e to the negative n minus 1, and I multiply by e to the positive n, because e to the negative n at the bottom means e to the positive n at the top. The negative n cancels out, and I end up with simply e to the negative 1. So my quotient can be rewritten n plus 1 multiplied by e to the negative 1, and the limit as n goes to infinity is infinity. And that means that the ratio test ensures that this is, or justifies, that this is a divergent series. For the third exercise here, we have something a little bit different from what we are used to. We are looking at the series where the sequence of general terms is defined inductively, in this case by the first term, which is 2, and a relation of induction giving an plus 1 as a function of an. Specifically, an plus 1 is 5n plus 1 divided by 4n plus 3 multiplied by an. So it looks like it may be harder to study this type of case, but in this case it's actually the ideal setting to use a ratio test, because what is given to us is really the ratio an plus 1 over an. Specifically, this ratio is 5n plus 1 divided by 4n plus 3. This is what the relation of induction gives us. And so we can easily get the limit of this ratio. Right? We have two polynomials of degree 1 in n. The leading coefficient at the top is 5, at the bottom is 4, so the limit of the ratio is 5/4, which is greater than 1. And therefore we can apply the ratio test to the effect that this series is divergent.